In today's video, I want to show you how I went about solving exploit number 14, Airdrop, found here on the Solidity Challenges repo. If you haven't already, go ahead, clone the repo, open it up in your editor. I'm over on the README, and it states that this contract is ERC20 with Airdrop feature, and there is a list of addresses that can claim the airdrop, and they show us our addresses. Our challenge here, hack this contract to get unlimited funds, and then they provide the command to run the exploit. All right, so over on ERC20 airdrop.sol, it starts by importing a handful of Open Zeppelin contracts. It inherits them, and the constructor just takes in an address as an initial owner. That initializes the ownable contract, and you can see the ERC20 permit, they have static data passed to them. We have a single state variable, which contains the Merkle root. We have three functions, pause, unpause, and mint. They're all guarded by the only owner method. And then they go ahead and they're actually overriding the update method. That kind of states it right here. So you have to override it for these two contracts. So again, we'll just disregard that. That is just a necessity. That really focuses our efforts on claim airdrop and verify Merkle root. So the point of this is to actually claim an airdrop and be able to get infinite funds, apparently. So as we go through this method, it takes in an owner and a receiver address, amount, and a proof. There's only two pieces of logic here. It's going to verify the Merkle claim, and then if it passes, it's going to go ahead and mint the amount to the receiver. Now, this claim here takes in the owner, the amount, and the proof, and then it creates a leaf node and with the account and the amount. Now that we have that leaf node, it's going to use it as part of the verification process. So it needs the leaf node, it needs the proof, and then it needs the Merkle root to try to regenerate that. If it passes, and indeed that account is found inside the Merkle tree, then this will be true. It won't hit this require, so it won't be false, and we'll be able to mint. And then the owner should be able to get their airdrop. So obviously that's not the case in this example. There is some logic that's been left out. So one that stands out here right away is I don't see any logic telling us if this user has already claimed. So obviously you'd want to have a guard in there checking if they've claimed. There should be a mapping up here in state, but there isn't. So that already tells us that you could use your proof and claim again and again and again. So that's one thing. But what if it's not you that's actually claiming and someone happens to have your proof and know it's your proof? As long as they have those two pieces of data, mind you, they also need to know the amount, then they can be the receiver. Because this receiver address, if you see here, I have it highlighted, it's only ever used to be the recipient of the mint. So you can take someone else's proof and claim it as your own, and it's going to mint to you. And technically, it's going to keep minting to you because, like I said, there's no logic here that actually stop a person from minting over and over again. All right, so that's the problem. So let's go ahead and move over to the test. Over on ERC20 airdrop.t.sol, we'll go through this. They give us the contract, a defined user address, the amount here, which is actually 5,000 Ether, and they give us an attacker address. In the setup here, they're taking an arbitrary address here and passing that as the initial owner when they deploy the contract. And then they call mint, and they mint a bunch of tokens. They have a get proof method here that simply does that. It returns the proof. We have a successful claim. So they have ran a test just to prove that it works. So we can skip that. Our exploits that happen down here, they prank us. We are the attacker. We get the proof, and we're to put our exploit right here. So my approach was really simple. Like, for instance, even before I go into it, if you look at what a successful claim is supposed to be, well, what they're doing when they call claim airdrop, they're passing in user. Okay. Then we go over here, claim airdrop, owner, receiver. So both these are supposed to be the user. Well, in our case, I'll just make the recipient the attacker. Like we said, there's nothing going to stop us from receiving the funds. And now the README was stating that hack the contract to get unlimited funds. Okay, well then I'll call this method and I'll call it in a loop. I just called it more than once here, and I believe actually, okay, we look at the assert. They assert that the balance of the attacker has to be greater than the amount times 5. Okay, so I called it 6 times just to pass this assertion. All right, so let's see this in action. We move over to the terminal. I've already preloaded the command. It passes, and we'll scroll up right here. Test exploited claim. We're pranked as the attacker. Again, we're inside a loop. I call claim airdrop. I call it 6 times, and it does indeed transfer the 5,000 ETH each time. The balance down here has gone up, and where's my final assertion? There it is. Assertion true. So we indeed passed this exploit challenge. So that was my approach to this challenge. I'm sure there was probably a couple different ways. I may have missed a couple things. If I did, point them out. I'd love to hear them and love to see your approach. Or if you simply want to talk about my approach, you can find my contact information in the details below. See you in the next one.